All right, so we're going to be covering this topic of titrating a strong base into a weak acid. This is different than what we've done before, which is to titrate a strong base into a strong acid, or titrate a strong acid into a strong base. So it's going to seem familiar in some respects, but it's going to seem completely different in other respects. So let's take a look at the case where the one that we're comfortable with, the strong acid, strong base combination. Okay, so in this situation, we're comfortable with the sodium hydroxide as our strong base, strong acid, and HCl, and they're going to fully dissociate and transfer protons. The acid will give up the proton to the hydroxide to form water and sodium chloride. And in this case, you know that the pH is going to be a pH of 7 because if you're forming water, water is going to have a neutral pH and sodium chloride is going to have no impact. So at the equivalence point, when you combine a strong base and a strong acid, your pH is going to be 7. That's nothing new because this is exactly what you guys were doing in the lab on Thursday. So it all should make sense to you. But let's change things up a little bit. Instead of having a strong acid, we're going to have a weak acid, and we're still going to stick with sodium hydroxide. Okay, so here we go. There's our sodium hydroxide. Here's our weak acid, which is acetic acid, water, and then we have this salt that's formed as well. So let's take a look at what happens here. In the first instance, we have our sodium hydroxide, which is going to fully dissociate because it's the strong base. Okay, there we have fully dissociate, strong base. And then right next to it, we're going to have our weak acid, and that is not going to fully dissociate. However, because it's combining with sodium hydroxide, even though it doesn't want to, it's going to be forced to completely dissociate. All right, so the sodium hydroxide, the hydroxide ion is going to steal the H from the acetic acid no matter what, even if the acetic acid doesn't want it to. Okay, so that's what I've essentially written right here. You might want to pause and note that. And then it's important to notice here, if you recall back from our group quiz, the conjugate base of a weak acid is actually going to be a strong base. And in this case, this is the strong base, it's sort of hidden in here. And that's because this is an aqueous solution that's going to form this, right? And it's this here, this ion is actually going to be the strong base. It really wants to accept a proton and return back to this. Okay, it wants to form the acetic acid if it can. The problem is, as soon as it does that, if there's NaOH around, it's going to be busted apart and it's going to go back to forming this combination of ions. All right, get that into your brain, make sure you understand that. So now, if you understand that, the next thing that might blow your brain away here is that when this reaction is complete, and keep in mind, I don't have the arrow going back in the other direction. It does completely drive towards the products. In other words, it goes to everything over on the right side. When the reaction is complete, it's not neutral at the equivalence point. It won't be neutral at the equivalence point because of this, right? Right here, this is a strong base right here, meaning that it's going to do what? It's going to accept protons. And the only way you can accept protons is to take them away from this. And if you take a proton away from a water molecule, you create hydroxide ions, OH minus ions, and so therefore you're going to have an abundance of hydroxide ions in your solution at the end of this reaction when this reaction is all done. And so that's why at the equivalence point, the whole thing's going to be slightly basic rather than being neutral. All right, so make sure you understand that. I'm going to go ahead and write that down below this here. And again, you're probably going to want to pause this so that you can write this thing down and understand what it is that I just explained. So let's see what this means in terms of the titration curve that would explain how the titration will behave as we start adding in a strong base to a weak acid. Okay, so let's map this out. First, I'm going to make a set of axes where I have the pH on the y-axis and the number of milliliters of the titrant, what we're dripping into the Erlenmeyer flask, on the x-axis. Okay, so there we go. We have this thing all marked off the way I want it to be marked off. So let me just scooch over here and make sure you understand what it is that we're doing with this titration. All right, so here we have inside the burette, we have the sodium hydroxide solution, and in the Erlenmeyer flask, we have our acetic acid, or our weak acid solution. Okay, so over here what I'm going to do is create a data table that shows the amount of sodium hydroxide solution I added from the burette, that dude right there, to the Erlenmeyer flask, and I'm going to be measuring the pH of what's happening inside this Erlenmeyer flask, which contains the weak acid. So I'll have a set of data here. Okay, so now when you take a look at what we have going on here, you shouldn't be too surprised that as I add sodium hydroxide to the solution, that the pH starts to go up, indicating that it's becoming more and more basic as you add more of the sodium hydroxide. No surprise there. Let's see what happens though when we go ahead and graph all this data onto the set of axes that I have right here. Alright, so what I have here with all these little stars, those are all the data that I just plotted from here onto this set of axes. And so now let me just go ahead and put my curve into this place to sort of connect it with a smooth curve so you can see what it's going to look like. Okay, so in a sense, this doesn't look unlike the curves that you saw in the previous screencast, except there are some key elements to it that are a little bit different that I want to make sure I point out to you. So the first area of the curve that I want to point out is going on right about, maybe actually continue right to about right there. And in this area, it's interesting because we have this sort of uptick. It's going quickly up. Oh, actually, you know what I didn't mention? Oh, Chang. At the very beginning, notice that the pH is actually not down at around 1 or so, and that's because it's a weak acid, so it's not going to have as many protons that have been ionized. So you're going to have very few hydronium ions to begin with, which is why the pH isn't down around 1 when you have the pure acid all by itself. All right, now that little blue thing, that's that upsurge that you see, followed by the leveling off, is actually a kind of an interesting thing because you can see that the pH is sort of resisting change in that blue area right there. And then when it continues from that uptick to along the, well, I wonder if I should continue that blue line. Well, I should. I'm going to continue it to about right here. All right, so what you're seeing there is a resistance in change to the pH that you would initially not be able to see if we were doing a strong acid, strong base kind of thing. And that's because there's actually a region here it's called the buffer region. So let me zoom in on here. And the reason why it's a buffer region is because it's just that. There's a buffer going on here. And in fact, let me scooch down here to explain what's actually going on with the buffering. So buffer region. All right, so in this situation here, what we have here is the sodium hydroxides dumping off a whole bunch of these hydroxides. But don't forget, you have this weak acid that's in the Erlenmeyer flask itself. And when that weak acid, it will actually combine with this, all right, to form water. So the hydrogen pops off here to form water, and then this base all by itself. So as long as you have a bunch of this stuff available, every time you add in the hydroxide ion, it'll get sucked up. It'll, in a sense, get sponged up. And that's why you don't see a significant change in pH occurring along this area that I've highlighted in blue. All right, then what we see here is the sudden change that occurs right along right here, right? This rapid change that occurs. And that's happening because we actually, let me back that up a little bit. Sorry, I'm going to go up to this area right here. And what's happening there is that the buffer capacity has been reached. And so that means you've run out of that weak acid that would normally suck up all the hydroxide, and now you're having a rapid change in pH. It shoots up really quickly until you get to this point, say probably coincident with this star right here, right? This area here is where you've hit your equivalence point. Now I want you to notice, where is that equivalence point relative to what it would be if you had a strong acid, strong base situation? Because look, it's not across from a pH of 7, it's across from a pH of almost close to 9 that you have going here. In fact, if we use that star, that was what, pH of 8.72 going on there. Okay, and then after that equivalence point has been reached, then it's going to continue along the way in the exact same way that you saw. It'll behave the same way as you saw when we were titrating a strong base into a strong acid. That's not going to be any different. At some point, the base is going to completely dominate, and then you're going to have a whole bunch of hydroxide ions in there, and it'll continue to, and then it'll level off eventually. But I just want to make sure that you understand that we have this region here, this kind of slow increase. It's not going up exponentially, and the buffered region associated with the weak acid being a buffer. You have an equivalence point that is higher than a pH of 7 before you go off to the normal behavior that we see associated with titrating a strong acid and a strong base. And don't forget too that this thing starts up quite a bit above a pH of 0 because it's a weak acid to begin with. Okay, so there you have it. It's kind of dense stuff here, but whenever you see this sort of funny shape here, you need to make sure you can recognize that this is indeed when we're titrating a strong base into a weak acid. Bye.